Hi folks, this is Nikhil and you are learning GoLang with me. In the last session, we have gone through the implementation of the tree traversal algorithms in GoLang. And now, in this particular session, I will be explaining the efficient way of traversing the binary tree with the help of the GoLang implementation. So let's get started. So we have three traversal: in order, pre-order and post-order. And then in the last session we have seen one of the implementation that is there in GoLang. However, I actually challenged you guys to come up with the efficient implementation in GoLang and then come up with your solution and then can discuss over the comments. And now in this session I'm posting the solution for the same. Now let's see how to implement the in-order traversal with the help of the stack that actually guarantees the time complexity of big of n. That is, if there are n nodes, then the traversal algorithm will not take more than big of n. So let's dive away straight in the program. Now if you see this example, the in-order traversal is 3, 5, 10, then 15, then 20, then 23, 24, 30, 50, 70, 90 and 100. So it also posts the numbers in the ascending or the descending order depending upon how you build your BST. Now in order to use stack and in order to have the big of n complexity, we will require the doubly linked list so that we can turn that doubly linked list into a stack. So the implementation is this way. So you know that we have to visit the left subtree, then we have to visit the node, and then we have to visit the right subtree of the node. So you start with the root node, you make the root node as the current node. Make sure that you are giving the pointer over here. This is extremely important, and then you can see that the current node is of type pointer. Then loop until the stack is empty. So stack is empty and the current node is nil. So because we are using the pointer, that's why we can see that the current node is not nil. So this is the OR condition that you can see over here. So condition is current node is not nil and the stack length is not equal to 0. Then next one is, if current node is not nil, then you push the current node on the stack and then you point the current node to point to the left node. So you make the pointer to point to the left node of the current node. So the current node now becomes the left of the root node, or let's say current node. So in our example, it's 10, 5, 3. So root node is 10. So current node in the beginning will be 10, and then because current node is not nil, that's why it will be pushed onto the stack and the stack will have 10. Then the current node will be made to point to 5. Then current node will point to make or refer to 3. So stack will have 10 and 5. Then in that particular case, when at that point of time of the execution, current node will be nil because current node 3's left child is nil, or there is no left child, so current node will become nil. In that particular case, else will be executed. So we will have stack.front, and then you will see that element will be 3 because we have 10, 5 and 3. So 3 will be at the top of the stack, 3 will be removed, and then 3's right child is pushed to become the current node, which is also nil. So that's why 3's right child, as it's nil, that's why again this will not be executed. And then you come to the else. In the else, you will see that element stack.front. So now this time around stack will point to 5 as the top, so 5 will be popped out. So you have the remove to pop out the element from the stack, and then current node will be 5, and then the traversal order will have 3 and 5, and then current node will point to the right. So in this case right does not exist, so it will be pointing to nil. And then again over here your condition will not be satisfied, and then you go into the else. Then over here element is equal to stack.front, so it will be 10 now. So 10's 10 will be popped out from the stack, and then 10 will be appended to the list. So now you have 3, 5 and 10, and then 10's right node becomes the current node. So now you have 50. So now 50 will be pushed onto the stack. 50 is not nil. 50 will be pushed onto the stack, and current node will be pointing to 20 there. Then again similar thing will happen, and then in subsequent iterations we'll see that 15 will be pushed onto the stack, 15 will be popped out from the stack, and then 20 will be visited, 20 will be popped out from the stack. 20's right child is now current node. Current node is not nil, so 24 is added onto the stack. 23 will be visited, then 24 will be visited, popped out. 30 will be visited and popped out. Then 50 is the only one that remains on the stack, so 50 will be visited, and then 50's right child is onto the stack. 100's left child is added onto the stack, and then 70, which is 90's left child, is added onto the stack. At the end of this round, there will be 3 elements on the stack: 70, 90 and 100. Then you will pop out 70, visit that node, you will pop out 90, visit that node, and finally 100 will be popped out from the node, from the stack node. So if I execute the program, then you will see that you get the data in the ascending order. So 3, 5, 10, 15, 20, 23, 24, 30, 50, 70, 90 and 100. And this can also handle the duplicate keys. For example, if I have 50 couple of times, then you will see that you will see 50 couple of times, 50 followed by 50. So now for example over here you'll see that 50 is getting displayed twice, because this is a duplicate case, and it requires additional logic to cover this particular case. So that's the in-order traversal. Pre-order traversal, as you know, you visit the root node followed by the left subtree and then the right subtree. Now this is very simple to implement using stack. You create a stack, you push the root node onto the stack, and then you start iterating until the stack length becomes 0. Then you'll take a look at this top of the stack. It's just the pick operation. So you get the element, you remove the element. Now this is the actual pop, and now you cast the element to node.node. Remember, we are not using pointers over here, because over here you do not really require pointers to be used. So current node is your root node, you visit that node, so you add the node to the traversal order. Then you check whether the current node's right is not nil. This is important. Generally what happens is you always look at the left first and then to the right, because we are using stack and not queue. That's why you need to take a look at this particular line and then understand why it is really used at this line and not and above the current node left not nil. Otherwise generally you will see that if is this particular if which is checking the left subtree of the root node, or let's say the root node or any node, is before the if condition that checks for the right subtree. So you put the right child on the stack, and then you check whether the left child exists. If it exists, then you put the left child on the stack. Then again you check for stack length is not nil. Now 10 is already out. If I go with the example, then you will have 5 and 20, 50 on the stack. 5 will be at the top, because remember that we have used 50 before 5. So 5 will be on the top of the stack and 50 is at the second level. So now 5 will be popped out. 5's left child is checked, right child is checked, like this one. Again right child does not exist, so this will not be executed. However, left child does exist, so this will be executed, and now the 3 will be added to the stack. 3 becomes the top, because 3 and 50, again 3 is in the front, 50 is the next, so 3 becomes the top. 3 is visited, 3 is popped out. 3 is left child and right child do not exist, because 3 is a leaf node. So finally at this point of time, after 10, 5 and 3, you have only one element, 50, that is on the stack. Then 50 is popped out. 50's left child is checked. Before that right child is checked. Both of the right child does exist, so 100 is pushed onto the stack, followed by 20. So at this point of time, 100 and 20 are on the stack. 20 is the at the top. Then 20's left child is now the top. So what happens is you pop out 20. 20's right child is pushed onto the stack. 20's left child is pushed onto the stack. 15 becomes the top of the stack. Then you at this point of time you have 15, 24 and 100, right? Don't lose 100 which is on the right side of 50. Now 15 is popped out. 15 is a left child, so 24 becomes the top. 24 is popped out. 30 is added and 23 is added. At this point of time you have 23, then 30, then 100. 23 is popped out, 30 is popped out, and then you go to 100. 100 is popped out. 100's right child does not exist, so you go to the left. So 90 exists, so you add that to the stack. It becomes the top of the stack. Then 70 is added, it becomes the top of the stack. Finally, because 90 is already visited, so you pop out and then you add 70. So 70 is added to the stack. It is removed. Current right is nil, current left is nil. That's why stack length is becomes 0 and you come out of the loop and you get the traversal order. So if you see the pre-order traversal, then you have 10, 5, 3. So 10, 5, 10, 5, 3. Then you have 50, 50, 50, 20, 15, 24, 23, 15, 20, 50, 20, 15, 24, 23, 30. Then 50, this is the additional element that I added intentionally just to demonstrate, right? So let me remove that and run this again. Yeah, so now 10, 5, 3, 50, 20, 15, 24, 23, 30. Then you have 100, 90 and 70. 100, 90 and 70. So that's the pre-order traversal. Now let's talk about the post-order traversal. Out of these three, post-order traversal is a little bit tricky to do with the help of the looping and at the same time having this goal of having the efficient algorithm which can complete the operation in big O of n. So that's why we are using two stacks over here. So let me just explain the theory of two stack. So let's say when you want to traverse in the post order traversal fashion, then what happens is you cover the left subtree of any root node, then you cover the right subtree of that root node, and then only you visit the root node. That's how the sequence is. So that's why you require to make use of two stacks. You can achieve the same in one stack. However, that code is a little bit complex. So that's why if right nowadays memory is not that expensive resource, so that's why you can afford to hold two stacks. So you visit 10, you add that in the first stack, then it is popped out from the first stack, it is added to the second stack. Then you go to the left, you add 5 to the first stack, you add 50, you go to the right and you add 50 to the first stack. So now on the stack 50 is on the top, 5 is at the bottom, so second level. Then in the next iteration you pop out the top, which is 50, and 5 will remain as it is. So 50 is popped out, 50's left child is checked, it does exist, so you have 20 and it is on the first stack now. And 100, which is the right child, it is also added to the first stack, whereas in the second stack you have 10 and then 50 is popped out, so from the first stack. So as soon as you pop out any element from the first stack, you add it to the second stack. That's the general rule. So now 50 is added to the second stack. So in the first stack you have 20, you have 100, 20, 5. Then you query the top of the first stack, you get 100. So 100 is 100's right child does not exist, so left child is added to the top of the stack, first stack, and then 100 is added to the second stack because it is popped up. So this continues. So what happens is you unwind the tree in such a way that you cover the left subtree afterwards, and before that you cover the right subtree. So for any subtree, so for example in this case, because 100 is not having the right subtree, that's why you will see 100 getting covered first, followed by the 90, because over here again 90 does not have the right subtree, so 90 and then 70. Or in case of 50, you will see that first right subtree is getting covered in a sequence that you cover the right subtree, then root node, and then the left subtree. So for example in this case you will see that 100, then 90, then 70, then you have the root node. So now the left part is getting covered. In the left part also you start from the 30, then you cover 23, 24 and so on. So now what happens is your order is, you want to have the order of 3, 5, then 15, 23, 30, 24, 20, then 70, 90, 100, 50 and then 10, right? That's the order. So that's why you will see that you have the two stack, right? So traversal order stack and then the normal stack, then you push the root node to the list or the stack. There is a typo. Then you iterate until your stack is empty. You pop out from the stack. It's just a pick operation. So you become you mark this current node as the value of the element which is popped out from the stack or top of the stack, and then you remove the element from the list or the stack, and then at the same time you push that element to the traversal order stack. Then you check the current left is not nil, then current left is not nil, so you push that onto the stack, and then you push the right onto the stack. So current node right onto the stack. So you can see that as I was explaining, the right becomes the top of the stack, and then you unwind the right subtree first before unwind the left subtree, and this is true for any of the order or any of the level of your tree. Then you check whether the traversal order stack is not 0, and then because over here at this point of time you have finished the traversing part, but now you want to retrieve the elements in the reverse order. So that's why you want to go through the stack. You could have just used slice and then you could have reversed that slice. However, it's okay because I really did not know to cover how to reverse the slack in GoLang. So that's why slice in GoLang. So that's why I used two stack theory. Then you start with the traversal order stack from the front. You pop out the elements one by one, and then you just add the element to the slice. So it is nothing but the reversing your stack. That's it. Or it is nothing but the reversing your visited order, the order in which you visited the nodes. So basically at the end of the algorithm we will get the order like this. So you have 3, 5, 50, 3, 5, 50, then 23, 30, 23, 30, 24, 20, 24, 20, then covering 70, 90, 100, 70, 90, 100, and then finally covering the 50, finally the 10. Right? So root node is always at the end. So for example, in each of these subtrees you will see that root node is getting covered at the end. So in case of this 2, 3, 5, 5 is at the end. In case of this 3, 3, 5, 10 is at the end. In case of this 3, 70, 90, 100. In case of this 23, 30, 24, 23, 30, 24. Then in this case we have 15, 23, 30, 24 and 20. So that's why this order 15, 23, 30, 24 and 20. In case of this big, you have 15, 23, 30, 24, 20, 70, 90, 100, 50. So we can see this. and in case of the whole tree you will have 10 at the end, right? So that's the efficient algorithm to implement the tree traversal. So this is the efficient implementation. It takes big of n because you are iterating over the nodes only, that's it. Backtracking operation is very less, and that's why this algorithm or this implementation is big of n. Make sure that you are using pointers in GoLang wisely, because pointers are really the key. Pointer is key in GoLang, and sedulously make use of the reasoning process, so that at any point of time you do ensure that your algorithm is either the linear time or the sublinear time or the logarithmic time, and not beyond the quadratic time. That's it for now. See you in the next session.